So here's our topic. Here's our objective. I want to review a couple things. Radiometric decay is the process for something like uranium turning into lead. Happens naturally. It's truly spontaneous. It just happens on its own. And half-life is the time it takes for half of any sample to undergo decay, right? To give you a little visual, if I had 100 atoms, one cycle or one half-life, I'd have 50, then I'd have 25, 12 or 13, 6, 3, 2, 1, and none. All right. Something that's what half the K would look like. Now, with kinetics, there's an interesting equation that comes up if you look at several different samples. We're going to look at 3. I tried to choose random amounts and random half-lives, although 2 of them are very similar. That's going to help generate an equation, as you'll see in a minute. So if I wanted to understand this on a kinetic level, I'd want to know the order of these things. And you remember that I'd look at the reaction data, especially the concentrations, and I'm going to make 3 graphs. All right, one for the first, second, or 0 order. And I want a linear relationship. All right, so I'm going to look at my data. Here it is. I had more data. I did this out until I had none, actually. So I did it for like 100 seconds. And I made, here's the graph. You can clearly see that it's not 0 order because this is total, the blue dots are not linear. So the next one I'm going to look at is first order, the natural log. Whoa, that's clearly linear. Let's see if it holds true for the next one. And look, it's clearly linear. It does. And the third one, once again, it clearly is linear. So this allows us to make the jump to the conclusion there. No matter the sample, no matter the half-life, it's all going to be first order or the isotope. I want to call your attention to something you may have already noticed. It's these slopes. It's basically the same number. It's off by a power of 100 or 10 rather. It's off by a power of 10, not 100. We're going to compare that to this one. All right. So we've got this slope and we've got the half. There's my K. It's just the negative value, the half-life. Here's the second one. All right. This is a 4th set of data. It's not one that I graphed, but this is like carbon dating. And the final set of data is this. All right. Once again, you'll notice these 2 are very similar. Look, they're off by a power of 10. Now, I'm going to take these 2 factors and I'm going to multiply them. I'm going to get the same product. See, does that work on the bottom? Yes, it does. Let's look at the other 2. There you go. I get the same product every time when I multiply the half-time times the rate constant. This allows me to generate this equation where the half-life is that value divided by your rate constant. All right. This is going to allow us to do some calculations with any sample, radioactive sample. If I wanted to know the rate constant, I know the half-life, I can simply use this formula, all right, and plug things in. I'm going to plug it in here and then divide both sides by that and multiply both sides by K, and I'm going to get K is equal to those 2 things multiplied together. So I get the rate constant is this. That means the molarity changes that much every year. It's not a big change, but look at its half-life. It's enormous. All right, thank you, and let me know if anything I can do to help. All right, bye.